what about if we've got another functional group that actually takes priority over the thiol? Like in this chapter, for example, we have an alcohol. So what you're going to do is you're basically going to name the thiol functionality as a substituent, giving the alcohol, in this case, priority. So in this particular case, we have our thiol group hanging off of the first carbon, actually the second carbon, because we're going to give priority to the hydroxyl group. And we're going to use the word mercapto instead of thiol. So this is going to be some sort of ethanol, right? And this would be 2-mercapto ethanol. Let's see. The next one, let's number these. So if I go from left to right, 1, 2, 3, 4. Or from right to left, 1, 2, 3, 4. So it looks like the green path puts the hydroxyl group on the lower numbered carbon. So that means that the mercapto group is actually going to be on the third carbon. So this is going to be 3-mercapto-2-butanol. All right, so now we're going to talk about the reactivity of alcohols. And it's important to start out, I guess, back a little bit in general chemistry, talking about the polar covalent bond. So you guys remember, let me draw just a simple alcohol here. So we'll just draw methanol. And I'll exaggerate this bond a little bit for you. You've got 2 lone pairs of electrons on that oxygen. There is a dipole moment going in this direction, right? Which would put partial negative charge on the oxygen, partial positive charge on the hydrogen. And another thing that's important to notice is that the electrons are sort of localized on the oxygen, right? So the lone pairs are sort of localized on that oxygen. They're not sort of decolocalized across the rest of the molecule. So we've got this partial positive charge on that hydrogen, which makes it weakly acidic. And because those electrons are not sort of being yanked in another direction, or we don't have a particularly powerful electron withdrawing group on the carbon next door, like a fluorine or something, right? So that partial positive charge is not gigantic, and it certainly isn't a formal positive 1 charge, but it's a partial positive charge all the same, right? What does that mean? The electrons are not being shared evenly in that bond. That's a polar covalent bond. The oxygen is hogging the electron density, right? So the electrons are not being shared evenly. That partial positive charge on the hydrogen makes the alcohol weakly acidic. We also know that we can hydrogen bond with an alcohol because we can have these guys hydrogen bond with themselves. They can hydrogen bond with other molecules that can also hydrogen bond, like water or amines or whatever, right? So, and you remember the requirement for that, right? You've got a hydrogen directly attached to some electronegative atom like oxygen or nitrogen. And hydrogen bonding is one of our stronger intermolecular forces. So this is important stuff to remember. The localization of the electrons is also noticed in the conjugate base. If these are, so let's just draw ethanol here. So if we were to deprotonate this alcohol, like with some group 1 metal hydroxide, like sodium hydroxide or potassium hydroxide or whatever, we would take that hydrogen off and it would dump its electrons onto the oxygen. And so you'd get the anion, right? And say H plus over here. So we started with ethanol. And over here we have the ethoxide ion. Again, though, those electrons are localized on the oxygen, right? So they can be used, well, the ethoxide ion is going to be a pretty decent little base, right? We've got a weak acid, ethanol. Its conjugate base should be fairly decent, right? Remember from Gen Chem, if you've got a strong acid, its conjugate base is weak. And if you've got a weak acid, its conjugate base is strong. And we can use those electrons as either a base, right? Or we could use it as a nucleophile. Remember in the last chapter when we were talking about SN1 reactions, we used methanol a lot. Just remember we were talking about competition between substitution and elimination reactions. And we settled on, you know, if you want to favor the SN1 process, you want to have some nice poor nucleophile or some weak base, right? Preferably something bulky. And so what if we started out with this as our alkyl halide? We'll just keep it simple and have all these be methyls. We'll just let the halogen be X because it doesn't really matter. If it takes off though, we get a carbocation. And in this case, we're going to get a tertiary carbocation. And this is where we used methanol a lot when we were talking about SN1 reactions. This is one of those situations where it's kind of nice because you can use the methanol as both the solvent and the nucleophile. But so now check it out, because we're using those localized electrons, right, the lone pairs on the oxygen, as a nucleophile. That thing is attacking the electrophile. You know, I should probably draw this like this. This is your rate determining step. So this is the slow step, right, in the SN1 process. That's the taking off of the leaving group. So that's our slow step. And then the nucleophile is going to come in. This will be faster. And the oxygen of the methanol is going to bond with the carbon. We'll have a positive charge on the oxygen. And probably some methanol or whatever you got going on in here is going to come in, take that hydrogen away, and return the electrons to the oxygen. And now what you have is a totally different functional group, right? You don't have an alkyl halide anymore. We talked about these briefly, but we haven't actually covered ethers yet. So you got an ether here, right? And this is basically just the business end of this process. Yes, there's, you know, some byproducts hanging out or whatever, but we've basically used our alcohol as a nucleophile. So those localized lone pairs of electrons on the oxygen can be used as a nucleophile in this SN1 process anyways. But so